Hi everyone and welcome. Every time you use an app, stream a video, or access a website, you're using electricity in a data center somewhere in the world. In fact, data centers consume about 1–2% of all global electricity. But what if we could be smarter about how we use that energy? That brings us to the key problem we wanted to solve. The carbon footprint of the cloud isn't static. The electricity powering a data center in AWS US East 1 might come from high carbon sources during the day, while a data center in US 1 is running on clean. So, our innovative idea was to ask, can we make our applications intelligent enough to actively choose the greenest place to run in real time?
Our solution is Green Proxy, a smart API proxy that does exactly that. Instead of just routing traffic based on speed, it adds a new, crucial dimension: sustainability. The creativity here is in shifting from a passive to an active approach to green computing. We're not just offsetting carbon later, we're avoiding emissions as they happen. The potential impact is huge. We can directly reduce the environmental footprint of our digital infrastructure, request by request.
Hi, in this video we are going to talk about the architecture of Green Proxy. So, Green Proxy is an intelligent, lightweight API gateway built with Ballerina WSO2 cloud-native programming language. It sits transparently in front of your existing infrastructure and make real-time routing decisions based on carbon intensity data from global power grids. The beauty is here, we need zero code changes to your current implementations and very less performance impact, and we have maximum environmental benefits using this kind of a service. So let's deep dive into the architectural design of Green Proxy. Here we walk through the enterprise grade architecture that we have used. As you can see, the entry point of this is Amazon Route 53. C53 provides our DNS layer with latency-based routing to the nearest AWS region. This ensures optimal user experience while setting up the carbon awareness decision point. Then, the regional Green Proxy instances lived in each and every AWS region. For each region runs our Ballerina based proxy on ECS Fargate instances, which is fully managed by AWS and has auto scaling and highly available features. Then the proxy is a stateless and it can horizontally scales based on the demand. Then we have a integration layer which proxy seamlessly forwarded the request to the existing API gateway and preserving your all authentication, rate limiting and security policies. And we are not replacing your current infrastructure, we are enhancing and giving more environmental friendly impact for your every API request. And we integrate with the electricity maps API for real-time carbon intensity data across 2000 plus power grids globally. This data is refreshed by every 30 minutes and cached locally for the performance and to give the real-time feeling and real-time data of carbon intensity values. And the key architectural designs that we have taken here is we have a microservices architecture patterns. As you can see in this folder structure, each component is independently deployed and scales using AWS ECS Fargate, and we have an event-driven architecture uses Kafka streams to provide real-time observability throughout our dashboards, and we have multi-layered caching mechanism for using Redis cache for carbon intensity values and the geolocation values. We are going to discuss those things in further. And we have the circuit breaker pattern implemented to graceful regression when the carbon data is unavailable. So this is the request for typical request flow, as we previously mentioned, request comes to AWS Route 53 and it's forward the request based on the request policy that AWS Route 53 is configured, and it hits the Green Proxy API gateway. Then in there we extract the client IP from the request header and perform the reverse geolocation and get the client location, intelligently map those location with the carbon intensity values. Then we evaluate the carbon intensity values of each and every region to get the most optimal region that API request can manage. Then we checked the carbon intensity values in the Redis cached, or we call the API external API, which is electricity map, and we get the carbon intensity values, and we have a separate algorithm to check and get a decision what is the best region to process this request, and we forwarded that request to the relevant API gateway in that relevant region. That is the basic request flow of our Green Proxy application, and this is the basic logic or core logic of this application. Okay, now let's move on to a small demo. First of all, let's look at the several carbon intensity values in several regions. As the initial region, we are looking for AP South region, and it gives the carbon intensity values and other things, which time it is updated and what is the time it is created, using the electric map API endpoint. Region selection algorithms find out the best region based on these carbon intensity values. Let's look at what it's going to happen. These are the regions that API requests that can handle, and this is the recommended region which gives based on our algorithm. Okay, now let's move on to the front end of our application, and this is the place where you can see the current routing regions, the services are up and running, and what kind of requests that you get from your services. What shows the regions where the Green Proxy services are live, and this shows the carbon intensity values for each kind of region which AWS servers located. Part you can see how much saving you have done and the average latency that you get regions that your services are currently active, and in the below you can see the request flow. Then let's move on to the regions. These are the regions that your application lives. This is the interesting part. This is the real-time monitoring section that you can see each and every request that come to your API gateway shows here, and how the carbon intensity values and the health of each service.